Hey all, welcome to another podcast. And in this podcast, we're going to take a look at how to go about reading the datasheet and with an intention of understanding how an embedded engineer can just look at the datasheet or specification for a controller and then execute the Blinky program. And Rajat will walk us through this exercise, and the four of us will kind of chime in and add information or add questions on your behalf. So go ahead, Rajat. Do you want to take over?
Yes. So I guess we will first understand the significance of this activity. So one of the biggest difference that you will find once you enter the industry, and specifically if you enter one of these semiconductor giants like STM32, NXP, Microchip, TI, etc., is that when you were in college and you wanted to use any of these controllers and ever you face any difficulty, you will find a lot of content on the web, and a lot of times people don't even look at datasheet. They look for some sample code, look at some community bug like Stack Overflow, etc., and get details from there and move
Right.
on.
Right.
But this is one of the things that changes when you start working for them, because suddenly you are the person responsible for putting all those content over there. And
Right.
a lot of times all you have up to your resources is a couple of colleagues, a data sheet, and a board.
Right.
So and usually these data sheets are quite big. They may range up to 3,000 pages, and it's easy to get lost in details.
Right.
And
This one,
if you
for
start,
example, is 1,700 something pages.
yeah.
Yeah.
And what happens is sometimes when you start, if you start reading it from the first page itself, it may take you a lot of time to just get to your day zero, which is toggle up in.
Mm-hmm.
And so in this activity, we'll specifically look into what specific keywords to look into a data sheet so that you can
Mm-hmm.
get started with your device.
Yeah.
A big highlight that I would like to differentiate, that sometimes what happens is, so there's no standard how you arrange these data sheets. So there are
Right.
multiple concepts over here. The one concept is of a device family. Whenever these giants create a devices, they don't just create one device. They create a device family. That means there will be a lot of devices coming out which have a kind of a similar architecture.
Mm-hmm.
And what they do is they sometimes assemble all this device family to have a single reference manual. So, for example, the document that you are looking at is specifically related to STM32F4X device family. So what it means is, even though you have several devices in it, all of them use the same IP. That means the UART is same on all of them. It may be located at a different address. You may have four
Mm-hmm.
UARTs in one, six UARTs in other,
I
but
see.
the programming nature of all of them is same. It's just the integration is different in them.
Right. Right.
And if you want a device specific information, then you will have a very device specific data sheet. Like you will have a very device specific data sheet for STM32F407VG data sheet, which will tell you how they have integrated all these IPs into the device, and will contain the characterization information of the device,
I see.
like what is the rise time, what is the fall time, etc.
Mm-hmm. Mm-hmm.
And you will have multiple characteristics of the RC oscillator startup time, what is the recommended settings for pull-ups, resistors,
Mm-hmm.
capacitors, etc. in those data sheets. But if you
Right.
want any functional kind of details for a device, the reference manual will become your go-to.
Right. Right.
Hmm.
Yeah.
And Rajat, just for completeness, can we also shed light on how do we find those data sheets? Is it as easy as just Google searching uh, the family name, uh, or
Uh,
let's say I get a hang on some board, some development board. How
yeah.
do I get what SOC is used in that board?
So usually what I do is I look at the SoC manufacturer, go to its site, and most of the SoC manufacturers have a search
Hmm.
button on their site. You can just put the product name on it and it will take you to
Hmm.
the references over there. And there you can find the
Hmm.
documents
Hmm.
for the device.
Hmm.
Mm-hmm.
But it's
So,
sometimes what happens is there are duplicate data sheets on some other vendor sites, like Element. You may find sometimes on Element 14, sometimes on some
right. Right.
known URL link.
Hmm. Hmm.
But I would say always go to the manufacturer side, because they will have the up-to-date data sheet.
Makes sense.
Yes,
Right.
Right. Right. Okay.
So Rajat, when you say datasheet, what does it contain? Like what information it has? Is it like the
so data
configuration of the IP or like the implementation of the IP?
so data sheet is the design, like English explanation of the device. So whatever
Okay,
you want to know
Mm.
about the device will be in its data sheet.
okay. And
Whatever
how to use
users,
that
As
device?
a
yeah,
programmer, right?
as a
Hmm.
programmer, yes, what you should be bothered as a programmer
Hmm.
will be in the data sheet. You will not find the details of
Hmm.
its
Hmm.
implementation in
Right.
the data sheet.
Yeah. Yeah.
Right.
Mm.
Yeah.
Where do I
Okay, so
find
maybe
that?
let's also find what? Find what? Like,
The
was that a
implement.
question or?
This.
Okay, they implemented. Okay, sorry,
No,
sorry, I
it was
missed
a
that.
rhetorical question.
Yeah, sure, sure.
Okay.
By the way, before we proceed, Rajat, which is why have we chosen this? And can you shed some light on that? In the sense, like, what processor
Chosen.
does this have?
That's one of the information you will look into when you get a device on your hand.
Mm-hmm.
And so the first thing you want to know, and if you can uh, go to the chapter down, can you
Okay.
scroll down a bit?
Mm-hmm.
Can you click on system architecture?
Yes.
So you have to find such chapter like this, where it will say device introduction or system architecture or memory and bus architecture, something like that. The reason we
Mm-hmm.
are looking over here is to find out which kind of processor it runs. If you go a bit up,
Mm.
Hmm.
you can see the first line. It says that it is a Cortex M4 based device with FPU, core,
Right.
iBus, DBus, and SBus.
Right.
So
Right.
now we know that what kind of device we have. Also, we will see
Hmm.
some kind of, it will tell you what kind of slaves you have, which is your memory controllers, SRAM,
Mhm.
flash memory, etc.
Right.
Right.
So how is it crucial to know
Hmm.
which kind of device you have? So each of these architecture, be it ARM, be it AVR, be it PIC, has a way in which they boot up. So you want to know
Mm-hmm.
which kind of device you are working on so that you can
Hmm.
follow that template of boot up. For example, for ARM, you need to set up the vector table
Mm-hmm.
Mm.
in the reset handler, and you need to
I see.
relocate. You need to locate
Hmm.
that vector table at an offset
Mm-hmm.
directed by the VTOR register.
Right.
So
Right.
this
So
kind
this
of
is
detail
the
is important. Yes.
right. I
Yes,
just
Krish.
wanted to kind of call out that this is the vector table offset register, right?
Mm.
Yes.
Okay.
I think in ARM it is called VBAR. I think.
Yeah. So
So you mean ARM
the thing
A
with,
because this is
yes,
also ARM.
Yeah.
ARM.
the
ARM
army.
A. Yes. Yes. Yes.
ARM A. Okay.
Yeah.
Okay. So ARM
So
A, it's called V bar. Okay.
yes.
Go ahead.
So the reason this is important is because if we don't put the reset, so when an ARM, just to go into a bit of detail, when an ARM Cortex M boots up, it expects that the first two words stored at the memory pointed by VTOR should be the stack pointer and the reset handler.
Okay. And you're
So we
saying
have to
word,
make sure, yes.
right? So 4 bytes.
So it will read the first
Hmm.
two words. The first word will be your stack pointer, and the second word will be your reset vector.
And what's a vector?
A vector is just a address to the ISR, that to the program that it has to execute. So whenever ARM boots up, what it will do is it will load the first stack pointer into its stack pointer register, and the reset vector into its program counter, and starts executing from there.
I see. I see. So this value then goes to the program counter.
Yes.
PC. Yeah.
Okay. Okay. Fair. And then the program counter would start to execute from there. And you're
Yes.
suggesting that that's how an M class processor boots. Copies
Yes.
the first word as the stack pointer and copies the second word into the program counter and starts to fetch the instructions.
Yes.
Mm.
Okay, perfect, perfect. Go ahead.
So, okay, now since we have this knowledge, the only thing we need to understand is where this VTOR is located. Where I have to where this VTOR is pointing at. So by default, designers will point this VTOR to something. It's not like it's a dangling thing. So it's a chicken egg problem, right? If VTOR is dangling, you will never be able to boot a device because you don't know where VTOR is pointing at. So
Right,
VTOR has to
right.
point at a defined location.
So
So
it has
the
a default
second,
value?
yes, so it will have a default value.
Okay.
Sometimes the device dictates that it will always boot from, and for that we specifically search for something called boot.
Okay. So do you
If
want
you
me
go
to
down, search,
Okay, I'll just do you want me to search or do you want me to scroll down?
just search for word boot.
Okay. So let's search for the word boot. Where are we searching? Who knows? Okay.
I don't think it searched anything.
Hmm.
Well, it did give me a
Okay,
chance.
okay. Anyways, we can scroll down from here. I think we'll end up on the boot menu somewhere.
Okay.
So if you keep scrolling down,
Mm-hmm. More.
yes.
Someday we'll get boot configuration.
Yeah.
Okay.
So
Okay.
if we look at this boot configuration, what it tells is so apparently STM32 has two boot pins which user can configure to select where the VTOR points to.
Okay.
I'm saying VTOR because I don't want to go into the details of boot ROM. Ideally, it points to boot ROM, and boot ROM scans these pins to decide which way to jump
Right.
precisely.
Fair.
But I
Fair.
don't want to
So
go into those details, and let's just abstract that these pins somehow decide what the VTOR will be.
right. Okay. Fair.
Okay.
Fair.
So if you look at over here, what it says is if the boot 0 pin is tied to ground, irrespective of what boot 1 says, we will always boot from main flash memory.
Okay.
And if it is set to 0 and 1, that means boot 0 is 1, then based on 0, it will either boot from a system memory or boot from the embedded SRAM.
Okay.
So why
Sure.
this is crucial? Because now we want to place our code specifically at this location.
Okay. Depending on the
So
pin
the
configuration.
depending on the pin configuration. So
So
we'll take the first case.
depending on
Yes,
the pin configuration, your VTOR would be pointing to that memory location, starting point or
yes,
something.
yes. If abstracted, let's on an abstracted way, yes. These based on this pin configuration, VTOR will either point to one of these memories, starting address of one of these memories.
And do we have? Well, obviously we do. Where are the addresses for these memory? Where can we look that up?
Yes. So we'll come up. We'll start looking into that. The first thing why this is crucial is because we want to put our code specifically in these addresses. So the next thing that is crucial is to figure out what is the address of these memories so that we can modify our linker script specifically to put our code over there. So if you go a bit up, we scroll through the memory map.
Yeah, this is the one, I guess.
Yeah, if you scroll down,
More.
okay, it would have been easy if we would have
Okay,
let's go to the starting. Yeah, go to
yeah,
the
this
memory
is the memory map.
organization.
Yeah, this is the
Go
memory
down.
map.
So this is FSMC, and we don't want the FSMC. Keep scrolling down. What we are looking for is flash registers. Go down. I guess we will have a specific section for flash. No, so this is the flash interface using which registers you can program the flash, not the flash memory within itself.
You want me to go to the
Keep scrolling down.
SRAM? Yeah. Okay.
Okay. Okay. So here we see a flash memory. Can you go down? Does it say scroll down?
Start address.
Does it say address?
No, doesn't say yet. Oh, I do see something, but SRAM something. No, it is not. Let me actually go before the memory map. I think it would have listed the banks. Let's see. Nope. Not listed.
So we are actually looking for flash memory over here.
Mm-hmm.
That's why I said
Rajat,
if there was
was
a search.
flash memory mapped in this?
Yeah, it will be
It
memory
should
map.
be.
Yeah, it is
It
just
would.
showing this memory map is just showing the peripheral registers and not the actually mem map.
Right. Not yet, at least.
Not yet, at least.
Okay, I think this is fun of browsing. Can you? Oh, okay. Here we
Okay,
go. Yeah,
so we see flash memory.
yeah, yeah.
So we
So
can see the
we
flash memory starts from 800
right.
000 to 80FFFFFF. So what we want our linker file is to have this address as the ROM memory
So we put our stack pointer and interrupt reset interrupt handler at this
into this
location.
at the start of this memory. So our code will start from 8000000, and so we need two kinds of memory over here, which is ROM and RAM in microcontrollers. You can completely go out of RAM, doing everything from RAM, and that's where we had the third option as RAM as well, where we can boot the device completely out of SRAM.
Right, but then SRAM would be the memory would hold the values on only until there is power supply.
Exactly.
In which case then, if the power is gone, the code is gone, memory is wiped
yeah,
out.
you need to flash the memory again and then reset the device.
Okay, perfect.
So that's why in flash memory we'll store some of the contents that are useful for us to restart, which is text section, data section, and I guess you only need text and data and read-only data, which is again part of the text section.
Yeah. Okay. Okay.
So, okay, we know how to boot up the device. Okay, now we are able to boot up the device. We are able to program the device. The second thing that is very crucial and need to know is the clock configuration, how the device is getting clocked. Because clock is like the heartbeat of the SoC. If it's not there, SoC will not, basically nothing will happen. And it is crucial to know what kind of clock you are running on. So if you can search in the data sheet, can you open the index?
Yes.
So IC chapter number 6 titled as reset and clock control. Can you click that chapter?
Yeah. Yeah.
If you scroll down, keep scrolling
More?
down. This is the domain reset. Yes.
Okay, I see this.
Okay, we can stop over here. And there's something called the clock tree of a device. And this basically tells you how clocks are sourced, how clocks are distributed, and how clocks are used across the device. So if you look at things on the left, the things on the left actually shows the clock sources. Not all of them are clock sources. If you see MC002 and MC01, this actually are the output pins, shows you the output clocks. You can bring the clock out on these and measure them.
I see. So we can hook these to the oscilloscope and we will see actual clocks. Okay.
Yes. So you can actually measure. So you can select, if you look at the a bit on the right, you can see there are two muxes to these pins, which are selecting which clock becomes part of this pin.
Okay, just a moment. I do see, well,
just on the right of these MC02 pins, you see two muxes over there.
I see this. I see this. Which one
upwards,
are you
Piyush. MC02, the pin numbers
upwards,
MC01 and MC02, just right to it. Upwards.
This is interesting.
In the same line where you see sys clock, LS.
This.
Or something.
Just a bit left to it.
Oh, damn. I'm blind. Yeah. I was like, okay, if we have
Rajat, one question.
Yes.
Yeah, go ahead.
Yes.
What is the need for the output clocks? Is it needed to provide a clock source to some other component, some other daughter board or something?
Not actually. So you can use them if you want to use that for the purpose, but the major use of them is for debugging purposes. Let's say you want to know what kind of clock you are running on. You can bring them out on the pins and measure them. So let's say you switch to a PLL,
Okay,
but
okay.
you are not sure what frequency you are running on. So these pins comes to your rescue.
Okay.
I see.
So one of the interesting things, and if we can remove all the scribble.
Right.
So irrespective of what SOC you are working on, there will always be an internal oscillator and there will always be an external oscillator to it.
Okay. So
If you
which
look
one's
into
the
this device, there is a box titled 16 megahertz HSI RC oscillator.
Okay, let me just look for that. I see
Just on
RC here.
Just
Yeah.
just keep going perpendicularly down, and you will see
Downwards.
the next box after that. Yes.
Yes.
So
Okay.
what it means, so there is a RC, there will always be an internal oscillator and there will always be an external oscillator. Devices in majority of cases will always start with the internal oscillator because that's a reliable way to start. Because you don't know whether the external clock is there or not. And let's say in case external clock fails, there should be something that can keep the device running to report such failures. So there will always be an internal clock over there, and the device majorly boots from this internal clock.
Okay.
Okay. If you want to be sure, in the same set of, I don't want to go into the register details, but if you go into this chapter, you will have registers, and in registers, there will be a register that selects which clock is the system clock.
Right.
And you will find that the default setting selects RC oscillator.
I see. Right.
The major thing that you should look into these devices is one, which is the source. And the second thing, which is very important, is how your peripheral is getting clocked. Because what we want to run is, for the day 0, we want to toggle a pin. And to toggle a pin, you need to access the GPIO peripheral.
Correct.
Now, the GPIO peripheral needs to be clocked. And what you want to know from this clock tree is how the clock is coming to GPIO. So if you look into the extreme right, you can see APBX peripheral clocks. And what you can observe from here is that this clock is a result of an AND gate, which has an enable bit and the clock coming from the system.
Right.
So what this is called a clock gating. That means your peripheral is clock gated. So unless you enable the peripheral, unless you enable this bit, your peripheral will not get clocked. And you will not be able to access the peripheral. And this is very crucial to know, because sometimes it is wrong to assume that your peripheral is, or as soon as you power on the device, your peripheral is getting clocked.
Right.
Because what happens is this helps saving you into static power consumption. So that's why designers clock gates the IPs.
Right.
So,
which makes sense.
So now we know how to flash our device. Now we know how to enable any peripheral. And the third most important thing to get the blinky LED working is to know how to toggle a GPIO.
Right. Rajat, before we go there is, so I'm assuming based on what you mentioned, this clock is, always available, right? But then wouldn't we need to kind of route it from here down to here? I see that there must be some settings here that we need to do, these three. You're suggesting that. Go ahead.
The default is good enough for you. The default is good enough for you.
Okay. So we don't touch this path at all. We assume whatever default is coming this way, that's good enough, and we only focus on this, the enable part of it. Okay.
So if you look at the only thing that is
I think,
changing in the path. Yes, Mohammed.
The key takeaway for me from this was that most of the times the default settings are good enough unless we care about the speeds. But we only need to take care of whether that particular clock for my peripheral is enabled or not. Is that correct?
Yes. Yes. So all you need to know is how to. So all you need to understand is how to get device boot up and how to enable clocks to the peripherals, because you are using MCU to run sub peripherals. This is not a general purpose CPU, right? You cannot do any powerful arithmetics on it. So how do you So now we know how to enable these peripheral clocks, and I'm sure if somebody goes into and looks into the register, they will find a register that will tell you write this bit to 1 to enable clock to GPIO.
I see. Okay.
There will be this.
Okay.
You know what? Why don't we do an experiment? Why don't we
Sure.
look into the registers for this? Can you open the index again?
Yes.
Expand this.
The
Reset and
clocks.
turn clock. Go into RCC registers.
RC, where is RCC registers?
6.3.
161.
Thank you. Yes. 6.3. Yes. This
see.
is APBX clock.
Yeah, so let's
should
go into APB.
that
So I
is
see open anyone. Let's
6.1.
open APB1. Let's open APB1 peripheral clock enable register.
Hang on. I opened AHB. Okay, there it goes. Yeah. APB3.
Okay.
So this would be APB2 and this
This
is
is-
APB1.
So these are AHB, Piyush.
Oh, sorry.
These are not
Can't
APB.
read also. No, I saw
So if you keep scrolling down,
okay,
yeah,
here
just-
is the
can you scroll a bit up? Yes, let's look into the description of each bit. Can you go down?
Oh, here. Okay.
Yeah, so if you see,
We are looking at GPIO, right?
okay, I guess we didn't open the clock enable registers. We opened the reset registers.
Okay.
Can you look at the title of the register? Yeah, these are the reset registers.
Reset
Okay, you need to scroll. Yeah, so I see APB1 peripheral clock
Scroll
enable
down.
register.
What is the number?
6.3.13. 6.3.13.
Yes. Yeah. Okay. Done. 3.13. Yeah.
Yeah. So if you
Oh yeah, I
go
see.
down,
Enable.
yeah. So if you go into the bit description says 𝑈ART7 clock is enabled, 𝑈ART1 clock is disabled. And if you go a bit up, go a bit up at the register. Sorry, down. I guess. Yeah. Go at the register where it names the register.
Yeah.
Yeah. If you look at the reset value says all zeros. That means all the peripherals
see.
are disabled.
Right. Okay.
Right.
So when you come to this, so you have to make sure that you first enable them to access them. If you directly try accessing them, nothing will happen.
Also, I see an offset here. So what is this offset from? Some base address? Like obviously.
Some base address. Yes.
Right. And that base address would be of the RCC.
Yes. So if you go into the memory map, open the indexing.
Okay.
Go into second chapter, memory and bus architecture. There's a chapter called memory map. Click that.
Yes. And then within
so
this
here you
RCC.
can, yes.
Which is
so we need to find which is 4002800. So this is the offset from this address.
I see. So from this address, we add hex 40 to this.
Yes.
And whatever that address becomes, that's the register we were taking a look at.
Yes, exactly.
6.1. This one.
Yes.
Okay. Perfect. So now then in this, we should be looking for GPIOs, right?
GPIOs, yes. Now,
But
so
at
if you
least
can,
not
I
here.
think, yes. So can you go a bit up? Yeah, a bit up. Keep going up. I think GPIOs in here are located. Yeah, here is it. Here it is.
AHB. Okay.
They are located on the AHB bus.
Okay. Can we go back to the diagram once and maybe what was that RCC diagram, was it?
RCC, go to
Yes. So we are talking about AHB now, which I see is available here.
Yes.
So how would I know what clock is going to the GPIOs?
So it's the same map, right? It's the same map. If you go a bit up, it's the same map. There's a
same map in the sense the register map
in the diagram. So you want to know if GPIOs are located on AHB or APB, right?
Correct.
Yeah. So to find that, we need to go a bit, just clear this up, and we need to look into a specific. So usually there is a bus map over here that tells you which peripherals lies on which bus.
Oh, okay. I see.
Hmm.
I suppose I am understanding what you're suggesting. Let's see if I can just scroll through and something like so. No.
Yeah. So if you go into the memory map again,
Memory map.
yeah. So open the memory map, go down, and just search in the memory map for GPIO,
Okay, I see.
and you will see the bus where they are located on. So if you look at all
Right.
the GPIOs are located on AHP1. So you need
Right.
to write to AHP1 ENR register.
Okay. Perfect. So we now know from this data sheet which processor, and then outside of this sheet we had some knowledge of how the CPU boots, which will come to in another podcast maybe. And then we figured the base address where we need to put our vector table, so to speak, this stack pointer and the boot address. Then we went about figuring out the clock that our peripheral would need, and then we are looking for, we found out that it's on AHB bus and then the GPIO. Okay, someone's at the door, but that's fine. All right. Okay. So sorry. AHB. Yeah. So which one should we be looking at? AHB2?
AHP1. AHP1.
AHB1. Yes. Okay. AHB1. And then let me go to the register. So this is AHB1, which is at the offset of 30.
Yes.
And so we would want to enable this GPIO.
Yes. A enable.
Okay. So we found out that. And again, the key point here is we are interested in the 0th bit in this register, and the register is at the offset of 30. And then from the memory map, we'll figure out the address of RCC AHP1.
Yes.
Right? Or actually this register. Yeah.
Yes.
Okay, cool.
Okay.
Where
so
to from
now
here?
So now we know how to enable the GPIO. The only thing left is how I can toggle that pin, right? So can you go to index and search for the GPIO chapter?
We want to search for the GPIO chapter. I see general purpose timers, general purpose.
It was up, Piyush.
Yes, general purpose IOs,
chapter
8. Right.
Yeah.
Okay, so
now things are very standard over here, okay, and they have to be standard. For example, if you are using a UART, you need to know how to enable transmitter, enable receiver, set up the baud rate, select the bit, and enable it, right? Similarly, for GPIOs, what you need to know is how to set the pin as output and how to drive that pin. So you want to know a lot of things about the GPIO, you can go through the whole chapter. Ideally, once you have this abstraction in mind, you can directly jump into the registers.
Right. And I see that they also have like a nice diagram explaining what's going on.
Yes.
Right. Okay.
So
and then
if you look at this table, this table tells you when the GPIO is output and in what mode it is. So it seems like I need to set the mode register to 01. If you look from the left side, output type to 1. And then based on whether I want pull up or pull not, I select that pull up and pull down. And based on that, I have the register. Based on that, we come up to a configuration. If you go down, I am definitely sure there will be an input configuration as well. If you scroll down a bit, so you will have the input configuration as well. So if you look at 00, where mode register is 00, you see that the IO configuration is input.
Where are you reading that from? Okay, 00 input.
Register.
Right.
Yes.
And mod register is 00. Right. Okay. Makes sense.
So what we know from here is that mode register dictates whether the pin is input or output. So ideally, I do what I do over here is, since I know I want to only toggle the output and toggle the pin, and I don't care much about much of the configuration of the GPIO, I directly go into the registers from here.
I see. So
Can
you set it to output like so,
uh,
or
so can
you
you go
don't?
into the GPIO registers?
It should be down somewhere, right?
Yeah, it's better to open index. It will be a big chapter.
Okay. I was wondering if they have like a summary page. So
No.
GPIO. Yeah, there was
And then
GPIO
GPIO register.
registers.
So as we
Just give me a
inferred,
moment. Give me a moment.
yes,
I'm thinking that these guys would kind of towards the end. Yeah.
yes,
Okay. Perfect.
yes, oh, yes,
Put
it's there.
everything together. Yeah.
Yeah.
So which one were you wanting to look at?
So if we look at the first is the mode register, and if we go into the
Mm-hmm.
mode register upstairs, we'll see that each GPIO has 16 pins,
Mm-hmm.
and bit number 0 and 1 tells how to modify pin number 0. That means GPIO A0.
Hmm.
So if you go up into the
Okay.
mode register,
Scroll.
scroll up into the
Okay.
mode
Let
register.
me. Okay. This is going to be challenging.
Challenging, yes.
Uh,
Ah.
okay.
And as we saw, if you look at the mode register, it says that if you write 00 to the bit field, it is input, 01, then it is output,
Hmm.
10,
Hmm.
then it is alternate function, and 11 is the analog mode.
Hmm.
So all I
Right.
want over here is to be an output mode. So I write 01 to this bit,
Right.
this register.
Right. And again, so this is the offset of this register from the
From the
GPIO,
offset of the GPIO A, the
GPIO
offset of the
A.
GPIO. Yes,
Fair.
which
Fair.
you can get from the
So,
memory map.
so maybe towards the end, once we have, so to speak hypothetically blinked the LED, let's just revise as to what all we did.
Yes.
Okay, cool. So we are going to write 01 here. Fair.
Okay. If
Then
you go
what?
down,
Hmm.
scroll down. So output type, speed, we don't care about these right now since we
Hmm.
just want to toggle the LED. Keep scrolling
Okay.
down.
Hmm.
What we are specifically looking for is how to drive this pin.
Right.
So pull up, pull down, we don't care much. Yeah. So now we are in the data registers.
Okay.
We want to specifically look at the output data registers because we want to drive the pin, right?
Right.
So
Right. We want to
GPIO
send something.
AODR, and now if
Hmm.
I want to write a one bit to it, that means drive the pin high. What I have to do
Hmm.
is write 1 to ODR 0 of this register,
Right. Okay.
and this will drive the pin high. And after some delay, I can drive this pin low, and we can toggle the pin this way.
Right. So when you write one here, the LED would kind of light up, and when you write a zero, then it kind of it's turned off.
Based on how your LED is attached on the board.
Okay, makes sense. Makes sense because sometimes writing a one might actually turn it off, and writing a
Yes,
zero might
exactly.
turn it on. Okay, makes sense. Makes
Yes.
sense. Cool. Okay, I suppose then we have completed the Blinky. So can I then go ahead and maybe revise what all we did so far?
Yeah.
So
Yeah.
we
Sure.
first, again, we some information that we know externally was the ARM-M, how it boots up. That information was like externally available to us through ARM-M's specification, which we'll go into later. But we figured information about the boot, specifically the address, right? And in this case, we happen to have some pins that decide which memory region it boots out of. And we just said that okay, it boots out of some hex 8 all zeros, right? That memory region. And then once we knew that, the intention is that we put our stack pointer and reset handler, those addresses starting from this memory region. And we then mentioned that this has to do with the linker script, which is a .ld file. Where then after that we looked at clock, and we wanted to enable the clock for AHB1, I suppose. And
Yeah.
then from here we went to the RCC section to figure out how to enable the clock to GPIO A. And then
Yeah.
after that we came down to GPIO a related address space, and then we kind of set the direction to output, and then from the data register we set it to 1 and 0. This
Yeah.
sounds good. Okay,
Yeah.
perfect. So now let's
So
go
one
about,
thing,
yeah. Mm-hmm.
so one
Go
thing
ahead.
we have to understand over here is GPIO is just an example. Let's say you want to do
Yes.
UART. You will end up doing
Mm.
the first three steps exactly similar. And now
Right.
GPIO will be replaced by UART, and you will do specific activities what you want to do with UART.
Right. Right.
Yeah.
That makes sense. Okay, so can we then go ahead and just take a look at all the addresses that we would need? And maybe with
Sure.
that, we can, close this podcast for today and take up another example next time. That
Sure.
sounds good? Okay,
Yeah.
perfect. So let me then go back to, oh, okay, page 1, maybe. Let's go
Memory
from
map.
here. Yeah. I mean, I just want to start off from like the first page if I at all I get there. Yeah, okay. Fine. So we are here. Then the first thing we do is go to memory map, right? So I suppose
Yes.
memory organization and memory map. We are looking for GPIO. We are looking for what? So we are looking for,
GPIO.
yes, we are looking for this address. We are looking for this address. Perfect. This is to enable the clocks, and this is
Yes.
to toggle the GPIO. Now
This to
within
access the
this,
GPIO peripheral. Yeah.
right. Okay. Yeah. Yeah. To access the GPIO peripheral and the reset clock controller
Yes.
in this case, right? And then
Yes.
from here, we need some offsets where the
Yes.
registers are, right?
Yes.
Okay. Now let's look at that. So we go to RCC. Okay. Where did I jump? Let's go to RCC, which is right here. And then within that, we wanted to go to
RCC
um,
registers
where is RCC
6.3.
registers? Yes. And then from
And
here, AHB.
you can no. So you can open it and expand 6.3 as well. At the end, you will find the summary of the all registers of RCC. Go down.
Oh, right.
Yeah,
Yes.
RCC register map.
Right. And we were looking for AHB clock enable,
Yeah. So
right?
yes, this is the one.
So whatever the RCC base address was, to that we add hex 30 and we come to this. And within this, this is what we set to 1.
Yes.
Right. Okay, perfect. So our clocks are enabled at this point, and then we go back to GPIO, and okay, within GPIO we go to the GPIO registers, and then we set the mod register to 01. So this was the 0th
Yes.
register from the GPIO A base
Offset.
from here. So we write 01 here. And then after that, we said we go to the data register,
Output data register. Yes.
yes, which is at the address of hex 14. So GPIO base plus hex 14. And to that, we write 1 and 0. And writing to that 1 and 0 would toggle the LED.
Yes.
Perfect. I think so. It would be very cool if we can also, in some video implement this.
Yeah.
Just as a complementary video to this one. Perfect. And I
Uh,
think with this, then we have
so we
logically
already,
concluded. Yeah, go
we
ahead. Sorry.
already have this video. We
Oh,
already have
nice.
such a video as part of the
Mm-hmm.
Renode tutorial. If you
Right,
look at the
right,
Renode tutorial, all we do is toggle the LED.
right. But we do so in emulation, just so that people know.
Yeah.
Which means we are not using a real board. It's just a software that is emulating the STM controller,
Yeah.
right? So we'll be able to verify the LED blinking through prints. Maybe what I'll do is I'll add the link for that video in the description. And
Yes.
perfect. Okay, so maybe we can then
At,
Mhm. Go ahead, Mohammed.
Okay, I think it's like
मोहम्मद भाई कुछ बोल रहे हो क्या?
I would like to add one point here. I think
Yeah.
all of the steps we mentioned, are kind of the same things which are happening under the hood. Yes, I think there is a
Right.
lag here at my end.
Okay, perfect. We can live with that.
Sorry,
Go
I'll
ahead.
start
Complete your
again. There is a
statement.
lag here.
Yeah.
Okay. So what I was saying was, I think all of the things which we mentioned here, or all of the steps which we listed here, are exactly the same thing which is happening behind the hood. In case of, when we use the platform development kit of any other platforms, for example, Arduino, we just peel the onion here uh, to see what is going on under the hood here.
Right. That makes sense. Yes. Mohammed, do you have more to add, or should I go ahead and conclude the?
I think you should.
Okay, let me
It's
do
a
it.
way.
Okay, I think then with
That's
this, we can wrap up the podcast for today, and
go ahead.
let's meet up next time with some. Okay, thank you. Let me just wrap up the podcast for today, and yeah, this seems like a logical conclusion to end the podcast at. Yeah. Okay. Thanks for joining in. See you guys next time.
Bye bye.